Ami körülbelül ilyen van.
4 is the power, so it's quite a small probability. Knowing the powers of 2 tells you it's a very small number. So what's the probability of having one more protrusion? I'm running out of prizes, so I'm not giving away a prize for this, but if you recall combinatorics from school, let's pick one protrusion on one dial and none on any of the rest. So that's the number you get. So that's 2 to the power of minus 24. So that's obviously 24 times the previous one, and so on. If you move 2 notches, that's at the power of minus 24. Binomial distribution will tell you that the maximum is reached at 12. So it's half of the 24. So protrusions in one half, no protrusion in the other half. And that's 16%, and it's way bigger than just moving one notch in one case. That's the binomial spread. The probability range from 0 to 24, and there's a peak at 12, and 9 to 15, it's nearly 90%. That's the probability of the number of protrusions you will encounter when you move the dial around. So we'll have to move on from this.
Annak, hogy egy támadó lát egy rejtjeles betűt, és ugyanaz volt.
What's the probability of a cracker encountering the same sign as the original? This is the probability. And what is the probability of the attacker seeing a sign, and you will have to subtract once? That's the probability. And subtracting 12 to get the original letter. So that's all you need to know. So OFPOB, etc. was what I coded. And if we subtract 12 out of O, that's the biggest probability, so that the original letter was probably C. And with some probability, it may have been FED as well. Because we saw, looking at the binomial distribution, and you continue on and on like this. So can anyone guess when I coded? So what was the original message? What was the original string? Well, let me give you a clue. The first letter was B. Who can guess? In Budapest. That's the word, Budapesten, which is Hungarian for in Budapest. So the problem is that the encryption key was rather unevenly distributed, and that was a problem. And Schemann's theory describes this, the entropial analysis of language. So it's 1.1 for this sort of encoding. So of the coded message, all you need to do is write out a table, and then you can guess what the original text was. So was this a successful machine? Who says that it was a success? So those of you who held up your hand when I asked if it was successful, who would say on this occasion? Well, one vote, another? Great. Great. That's very good. You stick to your guns, and that's a major achievement. Unfortunately, it was not a successful solution in terms of protecting information. I'm not aware that the Russians could crack the code, but I suppose that they were able to. So I would have used a different category. In the interest of time, I will soon have to conclude. Well, today's results point out that there are many Hungarian achievements in cryptography. There are current achievements as well. And these scientific achievements are mostly such But you know, that's the way science is structured. Lots of people bring little bricks to build the large building of science. And bricks are built one upon the other, and someone else comes along and makes a small contribution, and it very rarely happens that someone, a great genius, comes along and builds a whole new floor so that you reach new heights all of a sudden. But Hungarian mathematicians and engineers contributed in great numbers to this structure of science. They all had their small modules. Let me just mention a few. János Gonda, open key algebra systems and their features, and the LSH properties was one of the areas in which he did research. And one of the biggest cryptographers was Tibor Nemetz, and he was working with POP, data compression and security relationships, and Gábor Tardos wrote an academic paper on cryptography, and a lot of people refer to him, and István Vajda teaching at the Technical University, and decryption systems, linear approximation is his field. He's published extensively. László Csirmaz, Attila Pető, Gyula Katona, András Sárközi, and lots of others made modest contributions, but the biggest contribution by Hungarian researchers, I feel, was the following. And here's a short intro so that you get the full picture. And I also wanted to tell you this. We don't just have successful publications. Bruce Schneier yesterday mentioned hash functions. There's a new competition. You can submit proposals to replace the SH current standards, and we've seen cases. A research team of a countryside university submitted a paper on an SH proposal because the hash functions, certain features could be boiled down to the matrix mathematical functions, but unfortunately a publication soon appeared with conflicting points, so they were out of the competition. And this was an unsuccessful attempt to propose a new hash function. But I'll describe the following figure who was a lot more successful.
In the too large area of cryptography, that was mentioned by Bruce Schneier yesterday, and whenever he said historical examples, it belonged to the encryption of the old famous persons, and later on they remained cryptic, and now they became accessible in the public domain. But the public domain started a great development after Hellman's and Diffie, when they published new directions in cryptography. Hellman is the bearded one, and the other one is Diffie, and it appeared in the IEEE. These are the arisal of systems with double keys. Open communication, you know, the RSA system, the algorithm of Rivest-Shamir-Adelman, which appeared in '78, and there was another Merkel-Hellman kind of. Merkel is the bearded gentleman, hiding information and signatures in trapdoor knapsacks, which again appeared in the IEEE. There was a new crypto system, and that could read RSH for a long time. Exponential. The attack was under exponential time, depending on the size. That was the powering of large numbers and the multiplication of large numbers, and it was by orders of magnitude faster, up to the point when Shamir, during a research project, worked out a very effective attack further developed Lovász László's article. And now we have this LLL algorithm in which Lovász is involved. Is the basis of lots of cryptographic attacks and analysis, but with Lovász is
most is maradt ebben.
They put down the knapsack algorithm, and RSA is a counterattack against the knapsack algorithm. The attack time of RSA is a super exponential formula, whereas Lovász's algorithm is a kind of real-time hacker attack support. This is the biggest Hungarian contribution to the development of cryptography, which was a kind of breakthrough. Some words about the cryptic secret areas. Schreier mentioned yesterday, Bruce mentioned yesterday that he knew lots of things which moved into the public domain only later on. The English service MC5, MC6 used open key system based on factoring. Key identification protocol was already invented by Williams in 1974 and was used by the British Secret Service. And there are two closing slides. How we can provide our system with proper protection. In the state service area, in the state service, there is an authority. This is a kind of national security supervision, and there are government decrees from 2010 which regulates the operation of this authority, and there is also national supervision which licenses encrypting and the testing of encryptions. This is my closing slide. It is impossible to break into this house. The front door is 4 feet thick and made of solid titanium. That's an informatic system, an analog of an information system, because it has a very strong door. This is the cryptography in an IT system. We can prove lots of things, but Hacktivity is in the background. We can really circumvent and avoid a very, very strong protection with very strong cryptography. How can we protect our data? With the means of cryptography, we should use secure, strong algorithms which withstood all known attacks. RSA is good, and the first algorithm that I've shown you before is good, but if parameters are not appropriate, then they can be cracked. Proper choice of parameters, secure implementation, and of course a proper use of the system. Thank you for your attention.
Köszönjük szépen, remélem, hogy ti is annyira élveztétek, mint én.
Thank you very much. You have really enjoyed it.